So for example, nothing in that theory tells you what the mass of the electron is or how the quarks couple to each other. Those numbers are just observed in our universe.
Well, you said free numbers, you mean not predicted.
Correct, not predicted by the structure of the theory. Now, in contrast to that, in string theory, if you found a solution in string theory that produced particle physics like we see in our universe, none of those numbers are free. They're all determined by the configuration of these extra dimensions and the structure of the theory. So it's a huge array of physics that you have to get right all at once. And here I've been talking about particle physics, but you also have to answer questions about cosmology and the large-scale structure and history of the universe. So how are you going to decide if string theory is wrong? I think that it's most likely that we would be able to say that the structures that we see in nature, we can argue that we either can or can't get the right sort of regimes of numbers and effects that we already know are there much more rapidly than we're going to build an accelerator to see a string.
I love that.
Oh, that's...
Yeah. So what you're saying is whether or not you can test the dimensionality or the other sort of physicality of string theory, if your theorist can go in the back room and come out and say, I pluck this string this way, it's going to give me an electron and it's going to give me this mass.
Right.
And it's the only mass that's going to come out of this.
Right, because that's the right number.
It's the right number and the right vibration, and it's going to look like an electron. That's a Nobel Prize right there.